Alright, now we've done graphical analysis. We've seen how we can actually plot these functions and then use those plots to figure out the orbits at various points under them. Now the next thing is, since this is a grunt kind of task, we'll let the computer do it. For that, I've written another program in the same repository. It's called graph.py. It's got a few more command line options than the linear plot one because it does more, but it's essentially the same. So min size, min and max, just looking for the name of the function. Start and stop. You want to start plotting, like we want to plot the function now. It's not just the number line. You have to actually plot the function. So start and stop are the starting and ending x coordinates at which starting from and ending at where we'll actually plot this function. Right? So if I wanted to plot, for example, sine x from minus pi to plus pi, start would be minus pi, stop would be plus pi. Seed is the initial point. Iters is the number of iterations to plot, because some of them just explode and you want to keep iterating. You have control over that over here. I didn't put that as an explicit thing in the previous one. Alright, so with this, let's just try a simple thing first. Take graph.py minus min size equal to 1024,768 min equal to, let's just take minus 5 minus 4 to minus 4, max is 44, our function equals x squared, start at minus 3, because we have the graph. We can start at minus 4 so that we use the screen fully. Stop is also 4, stops at 4, seed. So let's see the quadratic function. Right? If we are below, what do you call it? Below, if you're at 1, let's start at 1. Let's see the fixed points first. And it is equal to 10 iterations. See this one, and 10 iterations. And see what happens. It just stays there. Right? It doesn't do anything. So it just stays at 1. Maybe I can just reduce the screen size a little bit so that you can see the console also. That's 600. So you can see that this doesn't really, doesn't change anything over here. It just stays at 1, so you don't see anything. However, let's try the same thing with 0. Doesn't change. You can't see anything. Let's try 0.999. Just below this. Now you can see how, just like I mentioned before, it comes from down here, down here, down here, like this, and goes over here. And it's reached 0.3. Let's just increase the number of iterations to say 50. You can see it goes and finally reaches 0. Right, this is 1, this point over here, where this x equal to y intersects the curve. So we don't have to actually go all the way to 4, 4. We can just say 1.2, 1.2, and say 1.2. Function is going to start then. Yeah, 1.2. So that we can see a little more of it. But you can see how the graphic analysis is done. We come here, we move to this. We come down from there, we move to this. Come down, 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 move to this. Finally it comes and reaches 0. So this is graphical analysis for a point, in this case 0.9, which is less than 1, right, on the curve y equal to x squared. Now, let's see what happens with, let's increase this a little bit. So let's just go a little bit up. Let's say 10. We need to clean up interface a little bit, but this was written quickly on a train, so stayed that way. Start from this, and the seed is, let's just say 1.0001, just above 1. Whoops. Okay, so let's just make it 10 iterations. It's too small. Let's say 15 iterations. Just one a little bit. 20 iterations. You can see how it's, it starts out from there and goes up from there, goes up, and just explodes. right? So this is the behavior of a point which is more than 1. So yes. Now, just because of this, there's 2 points which have come up right now. So now we'll just talk about graphical analysis and more types of points. If you notice something, the point which we first talked about, in this case, we had two fixed points. One was 0, which it stays fixed, and the other one was 1, which also stayed fixed. However, the behavior of these 2 points looked very, very different. What was it? So 0 is for f of x equal to x squared. 0 is a fixed. 0 and 1 are fixed points. Right? However, 0 is what's called an attracting fixed. Right? This is a new term which we haven't seen yet. What is an attracting fixed point? Well, an attracting a point P is an attracting fixed point if there exists some range, right? A less than some ranges, A less than x less than b, where for all points in all points x, right, the orbit tends to p. This basically means there is some range of points, close to p, where if you start checking the orbits of any point within that range, they'll tend towards p. They'll quickly come towards p. So p has the ability to sort of attract points within that range, right? And this range a less than x less than b is called the basin of attraction. Right? So if I were to, if in this case, so in our case, 0 is an attracting fixed point. Right? What does that mean? 0 is an attracting fixed point because, if I have numbers that are within, actually, for 0 is an attracting fixed point, and the basin of attraction, the basin of attraction is -1 less than x, 1. If it's within this much, if the modulus of x is less than 1, it will attract it. So you can see that. Let's say we tried it over here. Stop this, 0.9. Even if it was, so we did this, it came here. If it were, minus of this, minus of 0.99, if it starts from that side, it still goes from there. It starts from here, it shoots all the way here, and then comes down. So within this range, and within this area, this is called a basin of attraction. This much, if a point is there on this curve within this much, the orbit will finally come towards 0. That's the basin of attraction, okay, for this point. Now, we have this is called the basin of attraction. Now, so that's an attracting fixed point. Right? 1 is a repelling fixed point. What does that mean? Well, 1 is a repelling fixed point. This means that 1 itself is a fixed point. If you're on 1, you'll stay at 1. However, if you deviate even slightly from 1, if you move slightly above 1.0001 or 0.999999, you will never reach 1. You'll just get thrown away. You'll get pushed off. Right? This basically is the opposite of that. So a point P is a repelling fixed point if there exists some range A less than x less than b, where for all points in that x, the orbit will leave that range. Right? So the thing is, as you iterate, you just get pushed out. So this is what's called a repelling fixed point. And I'm not going to visualize this for you, but you can check out this function. F of x equals x raised to 2 minus half, 0.5. Right? This function has 2 roots. If you solve this, you can find the fixed points by solving this equation. You can say f of x equal to x, which is basically x squared minus x minus 0.5 equal to 0. If you solve this, you will get 2 roots, which one is 1 plus square root of 3 divided by 2, and the other one will be 1 minus square root of 3 divided by 2. You'll get these two roots. These two are the fixed points for this function. And what's interesting is that 1 minus square root of 3 divided by 2 is an attracting fixed point. And this is a repelling fixed. Right. And the basin of attraction is actually between minus of 1 plus square root of 3 divided by 2 and plus 1 plus square root of 3 divided by 2. You can try this out using this thing. I encourage you to try it out if you want to see this actually happen. Right, so this is the way these functions work. All right, so we this concept of an attracting and repelling fixed point, you cannot see them without using graphical analysis. The thing is you can actually see how these things happen using these. Now the thing is one of the interesting things is that attracting fixed points can actually be seen on the graph. What do I mean? Like you can just randomly try to plot the orbits of some points, and if you're within the basin of an attracting fixed point, the attracting fixed point will pull you in, so you can actually see that there's a fixed point. However, if it's a repelling fixed point, it's impossible to see. You cannot find it, right? Because if you exactly hit upon it by some fluke, you will find it. But if you're even slightly off, it'll just push you away from it. You have no idea that by subtracting or adding 0.000001, you would hit a fixed point. You can't see that if it's a repelling fixed point. So repelling fixed points are invisible; they're hidden. Attracting fixed points sort of advertise themselves, right? Especially one with a wide basin. Now, because of this brings us to another concept in this whole chaotic systems thing called stability. And this is actually one of the fundamental things in this whole business, right? The basic concept of stability is that an orbit is, a dynamic system is said to be stable if you can change for a value. If you can change the value just slightly. So the basic thing is slight, small change in initial conditions produce predictable changes in dynamic behavior. Right. That's basically the idea. If you change the initial value slightly, your function more or less, behaves somewhat predictably. So, for example, in our case, if we had this t of x equal to x squared, if we changed the attracting fixed point 0, if we go like 0.1 or 0.2 or 0.3 or something like that, even though we've changed it by just that much, it is stable. Right? So you can say that for t of x, for f of x equal to x squared, this is stable for modulus of x less than 1. Right? And also for modulus of x greater than 1. Why? Modulus of x less than 1, it's stable because, if you're less than 1, then for any value, even if you shift this way or shift that way, you will finally end up at 0, which is fine. Modulus of x greater than 1 is stable because even if you shift a little bit more this way, that way, you will reach infinity. That is fine too. It's predictable, you know that. However, 0 is stable. Right? Why? Because if you shift a little bit this way or that way, it's fine. And it lies within this. The thing is 1. 1 is unstable. Okay. So I can just put this. I can say that this is stable for this, stable for this, okay. Stable for 0 also, not unstable for y. Well, if x is slightly above 1, it goes to infinity. And if x is slightly below 1, it goes to 0. That's not stability. Right? We don't know. Right? We can't predict what will happen if that thing slightly changes. It might either go to infinity or it might just collapse to 0. So 1 is an unstable point in this. Right? As a general note, we can say that all attracting fixed points are always stable, because if you move away from them, they'll pull you back in. Repelling fixed points are not stable, right? Because if you move a little bit away, they'll push you off, right? And as a corollary, any point within the basin of attraction of an attracting fixed point is also stable. Why? Because if it's in the basin of attraction, you iterate over that, it'll pull you in, it'll finally reach the attracting fixed point and you'll get there, right? So that's fine too. So this is stability. And stability is important when you're discussing these kinds of systems. The basic problem what we're trying to solve is prediction. We want to know whether, you know, our mathematical model for, say, the weather is something stable. Right? If some slight change is there, if some drizzle happens somewhere, and you know, and a storm, like a catastrophic storm might result, then well, it's not stable. Right? Within that range of values, it's not stable. We should be able to predict this, and this is the thing. Right? So that's our discussion of graphical analysis to find attracting and repelling fixed points. Similar to attracting and repelling fixed points, we have attracting and repelling periodic points, which you know, is a similar idea, which is like it'll finally come there and it'll touch it, and then it'll start going. The orbit will start to repeat periodically. So this ends this segment. The next segment will finally show some more interesting uses of these graphs, and then we'll wrap up. Thanks.